Hello everyone, my name is HAOYU XU. Welcome to my video. And in this video, I will be presenting the result of PHYS1160 final experiments on planetary machine and gravity using PHET, gravity and orbits simulation. I explored how gravitational force govern orbits machine and how this principle related to Kepler's laws and Newton's laws of universal gravitation. I will now talk about Kepler's laws of planetary machine. Kepler's laws describes the machine of the planet around the Sun. The first law states that the orbits of planets are elliptical, with the Sun positioned at one of its faces. The second law tells us a line connecting planet to the Sun sweeps out equal arrows in equal intervals of the time, meaning that the planet moves faster when closer to the Sun and slower when farther away. Laws re-establish a mathematical relationship. The square of the orbital period is proportional to the cube of orbital radius. Formally, this is expressed as t squared is proportional to the RQ, or the equation on the screen. Now let's talking about question 9 about the center of the mass in the planet-moon system. Switching to the planet and moon simulation, the planet does in fact move slightly. It exhibits a small loop as the moon orbits. This occurs because both the planet and the moon orbits around the shared center of mass, or barycenter. In question 1, 4, and 9, which involves star and planets, the center of mass lies very close to the center of the star, due to the star's significantly large mass. In contrast, the planet-moon system, the center of the mass is located outside of the planet center, making the planet's motion are more noticeable. This difference highlights how relative mass affects orbital dynamics. Now to answer question 11, which is about interpreting scale in simulation. In a scale simulation which enables 2 grid lines, it reveals that every 2 grid marks represent 1 AU, which is equivalent to about 150 million kilometers, the average distance between the Earth and the Sun. Understanding the scale was essential for accurately adjusting orbital distance in the later stages of the experiment. Now to answer question 14, I measured the orbital period for 4 circular orbits at increasing distance from the Sun. Here is a summary of the table. At 0.25 AU, the planet takes about 20 days, completes the 4 orbits. At half AU, it takes around 17 days. At 1 AU, it takes about 368 days. At 1.5 AU, it takes about 785 days. This result confirms Kepler's third law. The square of the orbital period is increased with the cube of the distance from the Sun. The growth in the prod is not linear, which demonstrates how gravitational dynamics cause planets farther from the Sun to take much longer to complete the orbit. Question 15. The fastest orbital velocity belongs to Mercury, the closest planet to the Sun, and the slowest belongs to Neptune, the most distant major planet. This is explained by Newton's law of the universal gravitation, which states that the gravitation force between the 2 objects is inversely proportional to the square of the distance between them. Mathematically, orbital speed follows the relation of this equation on the screen, where g is gravitational constant, m is the mass of the Sun, and r is the orbital radius. Third, planet closer to the Sun must travel faster to counteract the stronger gravitational pull, while distant planets move more slowly. About my reflection on this experiment, this simulation made abstract concepts more easy to understand. I could see how gravity, velocity, and mass interact to create stable orbits. The experiment clarifies the importance of the orbit machines, especially how modifying velocity of distance affects the pace and the timing of the orbit. I also gained a better appreciation of the role of the centers of mass in dual-body systems like planet-moon and star-planet interactions. Overall, the hands-on visual approach improved my understanding of both Kepler's machine and Newton's gravity in a meaningful way. Thank you for your listening.